Okay, so this is our second part. So we were talking about differentiating computational modes from actually modes that belong to the physical system. So criteria for discriminating computational modes. So, since you're going to try to discriminate something, you have to have something that you know. And the thing that you know is not in the data, because if it were in the data, then we wouldn't have a problem anyway, right? What you have to do is you have to infuse the process with something new. And this information that is new is information that is a priori, right? What I mean by that? For example, in fact, anything, right, that is a priori knowledge about the physical system can be used to discriminate the computational modes. For example, let me be trivial here. If you know that the system is such, because you look at it and you have some engineering sense, you know that it's impossible that it would have a natural frequency of 1 hertz, let's say. 1 hertz is really slow, right? It goes back and forth every 1 hertz. Because you're looking at a plate and you know that that thing, even though you don't know the numbers, the smallest frequency has to be, 7 hertz. And you find one that is 1 hertz. Well, then you already know that one is not a real frequency, right? That must be a byproduct of the errors that we've made. So it is in this way that we operate, right? We are simply trying to see what information is there about the system that we happen to know beforehand. So we do know that damping is typically small. That doesn't mean that it is impossible to conceive a situation where a structure that you're looking at has high damping, but meaning high, meaning, maybe something with 15% damping in some mode, but it is highly unlikely. It's in typical structures, buildings, towers, bridges, and so on, dampings are in the order of 2-3%, 5% is already relatively large. So if we find, when we're doing identification, that we separate our frequencies and damping, and we find this mode and that mode have 20% damping, what are we going to do? We're going to say, forget about those. Those are computational modes. They cannot be real modes, right? So damping is typically small. So if the identified damping is greater than some limit, which you choose, we normally discard. And we say that mode is computational, right? I shouldn't say we normally discard. If the damping is more than the limit, we treat that mode as computational, not physical. That's one item. And I'm just going to talk about 2 of them. There are others, but when you only have output, these are pretty much all there is. There are papers that pretend to do something else, but in my opinion, at least in my view, they're just contraptions. They don't really add anything beyond what I'm about to say. The other thing that we use is what's called modal collinearity. Okay, what is modal collinearity? Well, that one is going to take me the rest of this presentation now, maybe 15 more minutes or something, and the next lecture that I will tape, I will continue talking not on the practical side of motor collinearity, but just to give you some theoretical background. For now, let's just focus on the intuitively simple aspects of this matter, right? When we calculate mode shapes in our system identification, I just remind you, since we are all kind of familiar now, let me just say that we would have something like this, right? AABB equals eigenvalues of A continuous, right? So once we do our system ID, we have A discrete. From A discrete, we get to A continuous, and this gives the eigenvectors and the eigenvalues, right? Now, the mode shapes are, the mode shapes are the matrix C times the eigenvectors AA. These are the mode shapes, okay? So you multiply, we obtain actually A discrete and C discrete, right? Assuming the output only. Then we get A continuous to be log of A discrete divided by delta T, right? And our C continuous is just our C discrete. Then we can take this is just a name, right? You can put whatever you want, but that name here is the eigenvectors of AC, and the mode shapes on the physical structure are just the C multiplied times the AA. I should say not only on the physical structure, but at the sensors, right? Remember, we are here in a system identification context, so it doesn't make any sense to talk about the mode shapes in some location where you don't have a sensor, because you have to operate under the premise that all you know about this thing is the data, right? So from the data we process, we get our discrete, we get our continuous, we do this thing, we get these eigenvectors, we multiply times the continuous C, and we get our mode shapes. Now these mode shapes will come in conjugate pairs, right? So there will be what we would call phi1 and then phi1 conjugate, then phi2 and then phi2 conjugate, right? Etc. So, assuming that we've ordered it in some particular way according to the eigenvalues. The important thing here is that, well, not the important thing, but just to say that when I'm talking about mode shapes, I'm talking about typically just one of the pairs, right? So if I say the second mode shape, I mean this one. If I mean the third, I mean the third. If you just count, that's 1, 2, 3, 4, 5, and so on, right? So these mode shapes that we calculate in this manner, they are in general complex. They're not real. They are in general complex. So the mode shapes come out, not just the fact that they are complex conjugates. What I mean is the mode shapes come out complex. So when you get a mode shape, let's say phi I, that mode shape, let me use three numbers, will be A plus BI, C plus DI, E plus FI. So using three entries for illustration, right? So the mode comes out complex. That's what you've got. Now, a mode shape is just a shape, as we've described before. So I'm not adding anything new here. We've described this already quite a few times. But since I can normalize this any way I want, I can take anything outside, I can take a look to see which one of these numbers is the biggest one, for example, right? When I say the biggest one, because these are complex, I'm talking absolute values, right? So I take a look at the absolute value of A plus BI, I take a look at the absolute value of C plus DI, I take a look at the absolute value of E plus FI, and I say, for example, okay, this one is the largest. So if that one is the largest, then I take that number outside and I just divide, right? This number became 1, and then this became A plus BI divided by C plus DI, right? And this one here became F plus FI divided by C plus DI, right? Now since a shape is a shape, I don't really care about this C plus DI that it's in front, so throw it away. So now that we've thrown that one away, let's see, where is my other marker, because this one is not doing so well. Excuse me for a second, let me look around. Here it is. Okay, so now to be clean, let's assume that this comes out to be 1, and since that was the largest, let's say this one was 0.7 plus 0.03i, and let's say this one was minus 0.4 plus 0.02i, for example. If that's the situation, then we say, great, these modes are so close to real that the imaginary part is irrelevant, right? So we don't have to worry about modal complexity. We just simply say our mode is 0.7, 1, and minus 0.4, right? Which is the way that we would calculate modes when we only use K and M, right? Because the modes of K and M, which are the undamped modes, they are always real. Once we put damping, one is not guaranteed that the modes are real, and in fact they are hardly ever real, but they are always, unless a special condition happens, which is what we will talk a little later and next time, they are almost real. So if the modes are almost real, we just simply normalize to the larger value and eliminate that little annoying part that is imaginary. It doesn't really matter hardly anything, and we say this is our mode, right? Fine. So you would say, look, if the modes are almost real in reality, and I go to my process, and I just did what I said I was going to do, right? I take C plus DI, I take it like this, but now I get something like this, 0.6 plus 0.3i, and minus 0.5 plus 12i, right? I would say, wow, that's a lot of complexity, right? That is significant. I don't think that that mode is actually a mode that is coming from the actual physical system. I'm going to take a leap here and assume that if my modes are not close to real, then it's probably because it's an effect of the noise that I'm trying to map input plus noise to output plus noise. So I would tend to also discard that mode. So what do we have as criteria? If a mode has too much damping, we throw it away. The mode and the frequency, right? We say that's not real. That's not from the real structure. And if the mode has too much complexity, after we've normalized it, we throw it away too. Now, okay, the issue, however, is that we need something more clean to decide. I mean, are we going to have to actually take a look at every mode, normalize, take a look, and then make a decision every time? No, we would like something a little more systematic. Not that it eliminates judgment, because in the end some judgment is needed, but we would like something that is a little bit more automatic. So what I'm going to do right this second is derive, it might be too much of a word, illustrate how we can very easily obtain a quantitative measure of how far a mode is from being real. So this is going to be called the modal collinearity index. And the version that I'm going to derive for you really is my own version. It's very close to the ones that have been published under different things. I don't think that there is any particular merit to mine or to the other one. They're all essentially the same thing. They lead to the same position. So we do it like this. Imagine that you had a real mode first. And notice that there is a little bit of an issue here, because the word real is used to imply the opposite of imaginary, that is, not the opposite, the other side of a complex number, but we also use it to mean it's of the real system, so it can be confusing. So I'll try to be clear as much as I can. So when I say this, consider a mode that it is a real, meaning no imaginary. Right? The ones that you would have from K and M. But because the modes come out arbitrarily scaled, maybe what we find is that our mode look like this. 3 plus 4i, 6 plus 8i, 9 plus 12i, right? So when we look at the output from calculating the eigenvectors of A and multiply it times C, we see something like this. But then we begin our process and we say, which one is the largest one? Okay, the largest one in absolute value is this one, so let's take that outside, and then let's divide by that, and we would get 1, and then this is 2/3, and this will be 1/3, right? And then we say, okay, that doesn't matter, and if I want to have it with the largest value, not the largest value, but this would be 1, this would be 2, that would be 3. I could show it like that also, right? So this is the mode. Therefore, this is the case of a mode that really had no imaginary, but it was trying to fool me because I saw it like this, right? When I do my process, I see that it is purely real. Now imagine that you take a matrix Q in which you list the real part and the imaginary part. Okay? The real part and the imaginary part. Now, what happens to that matrix is that that matrix, notice that there's no I anymore, right? So all I'm saying is you take a mode, the first column is the real part, the second column is the imaginary part. If you take a singular value decomposition of Q, you would find, as we know, right, a matrix that is first as big as 3 by 3, right? So we would have a 3 by 3. Then a matrix of the size of the matrix itself, which is 3 by 2. So that's a 2 by 2 with the singular values. That would be 0. And then we have a 2 by 2 here, right? So that's going to be the singular value decomposition of the matrix Q. Now it turns out, let's give these two singular values names, S1 and S2. For that matrix, we would find that the singular value S2 is exactly 0. Because the second column here is just the same as the first column multiplied times something, right? Times 4/3, right? So this column is equal to column 1 multiplied times 4/3. Right? And since the two columns are proportional, this matrix is of rank 1. And the rank is the number of non-zero singular values. So we would have S1 being something and S2 being 0. So what that tells me is that S1 and S2 can be used to tell me how, okay, in the case when the modes are real, it's always true that the matrix that lists the real and the imaginary parts is rank 1. Now, if the matrix is not rank 1, that means that there is some complexity in the mode. That is that once you normalize it, you still have some imaginary parts. So we can define the following. We can say, define gamma to be 1 minus S2 divided by S1, for example. What would happen? If the mode is real, this is 1, right? Because S2 would be 0. So for real modes, you'd get 1. S2 is always smaller than S1. At worst, it's equal, right? So the most complexity that you can ever have, which is when this is orthogonal to the first column, that's as complex as possible, then S2 is equal to S1, this is a 1 and that's a 0. So this thing goes from 0 to being really complex to, from 0 to being really complex to 1 being perfect. Now, to go along with what's done in practice, people like to multiply this by 100 and talk in percent. So we would say that gamma equals 100% means perfectly real. And as gamma goes down, then there is more and more complexity that cannot be removed. So if you are going to separate computational modes from real modes, from modes from the system, using this criteria, you have to put a threshold. And typical thresholds, as I said, you cannot eliminate the fact that some judgment have to be made. But for example, this is one that is widely used. For example, I expect this to be greater or equal to 90. So if this is more than 90%, mode is kept. It's possible, right? But for this less than 90%, we might say computational. Now, depending on the application, depending on the level of noise, depending on things like that, it might be appropriate to up that to 95 or to lower it to 85 or 80, depending, right? For that, you need experience to be able to make those decisions. But let's say before you achieve that, 90% is a useful threshold. So we have then, in summary, two things that can be used, or that we've mentioned in this class so far, to distinguish computational modes from physical modes. Now, I'm going to give you something much nicer than what I'm doing right now, but the idea would be this, conceptually. Imagine that these are the singular values of the Hankel matrices, right? And we get, remember your plots, so let's say you get something like this. So there is no real clear gap, right? Nothing huge. So you say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 11 or something. So you go like this. And you say order equals, actually let me say 10, so I don't complicate it with odd numbers on this first introduction. So I take the order of 10. So what happens when I take the order of 10? Each one of these things, then I get my matrix, right? I get my matrix, and from that matrix that is order 10, that means that we get an A1 that is 10 by 10, right? And let's say that we had 3 sensors. So then my C is going to be 3 by 10, right? Then we get our A continuous, that's also 10 by 10, right? And our C continuous is just the same as C1. Then for my A continuous, I get my eigenvectors and eigenvalues. So my AABB is the eigen of AC. And so we have that our lambdas is the diagonal of BB, right? Put them all in a vector because this is a matrix. And our mode shapes are CC times AA, right? So we are at this point now. How many mode shapes do we have and how many lambdas? Well, we have 10 here, right? And we have 10 here. But we know they come in complex conjugates. Yeah, as long as I did this with an even number. Sometimes you can have reals and then it's not purely complex conjugates, but let me not complicate it with that now. So we have these lambdas, right? So from our lambdas, we know how to calculate frequencies and damping, right? And so what we have is omega 1, omega 2, omega 3, omega 4, and omega 5, because they're 10, right? The other ones are the complex conjugates. And we have psi 1, psi 2, psi 3, psi 4, psi 5, right? So we have our 5 frequencies, we have our 5 damping ratios, and then we can calculate our gammas, our model collinearity index for each mode, like this, right? And so we have our model collinearity index 1, 2, 3, 4, and 5, right? Now we're going to say, what is computational? And we say, okay, let's say that this damping 2 or 3, let's say this damping was 0.12. So that damping is too large, so we might say frequency 3, mode 3 is no good. I don't care if everything else is good, it's just this damping is too large, right? Now, I may also say, when I look at 4, my order here is kind of ugly, so let's redo this thing again a little cleaner for you guys. So as I said, I have omega 1, omega 2, omega 3, omega 4. Omega 3, omega 4, and omega 5. We have psi 1, damping 2, damping 3, damping 4, damping 5. No way, this thing doesn't look right. Try the other one. Damping 4, damping 5. And we have our collinearity 1, 2, 3, 4, 5. Now here, let's say this was 0.022, 0.031, 0.12, 0.06, 0.01. So from the dampings, we say this damping is too large. So eliminate this mode, the damping is too large. Now let's say the collinearity index here was 99, 97, it doesn't matter what this one is because we threw it out for the damping, 81, and 73. Okay, so if we have something like that, then we would say these two collinearity indices are pretty good, but these ones are kind of low. Therefore, omega 4 and omega 5, we don't trust it either. Therefore, out of this process in which we took this order 10, which was 5, only 2 of the frequencies selected and of the associated mode shapes have satisfied the criteria that the damping is low and that the model collinearity is high. So we will keep those, and consider them to be the modes that we are sure, or reasonably sure, that they are from the physical system. Okay? Now, on the next class, I will present, well actually let me see, maybe I can do it in this class. Yeah, maybe I can do it in this class, at least to give the introduction to the idea. So, okay. So what is it that is not entirely satisfactory with the procedure that I just described? There's only one item that is not entirely satisfactory, which is that when we looked at the singular values and we said we see something like this, right? And we said 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we took this as the order, right? So we took an order 10. From that order 10, we ended up being able to keep 2. Well, actually I shouldn't say 4. Or let's say from order 10, which means 5 modes, we ended up discarding 3 on the basis of damping and model collinearity and kept 2. But the logical thing to think about this point is, what would have happened if instead of you choosing order 10, you had chosen order 12, or 14, or 16, or 8? Why was 10 the right number? And it's kind of hard to answer that question, right? Because there is no gap. There's no clear gap on the singular value, so how are you going to make that distinction? More troubling is the fact that not why shouldn't you take 12, because maybe there was another mode, but what if you chose 12 instead of 10, and then you still find that you can only keep 2, but they don't look that close to the 2 that you kept. So then that gives you, that throws away your confidence on the results that you are reporting, because the results are somehow dependent on the fact that you chose order 12. I mean, maybe I'm exaggerating a little bit, because that would probably be unlikely that it would change much. But the point is that we would like to do something that does not require that we make a decision with regards to the order. Okay? So what we do for that is then something called a stabilization diagram. Now, I think I am going to post for you, I mean, it's actually not a difficult thing to do by any means, but I'm going to post for you a program that I wrote a while ago that will actually plot the stabilization diagram. But what is the stabilization diagram? The stabilization diagram is simply a plot. In the vertical axis is the order. Okay? Now I am doing this stabilization diagram in a simple way. There are various versions, but you'll get the idea. Here is the order, and here are the frequencies that we get in hertz, let's say. So what happened when we did order 10? Let's say order 10 is here. When we did order 10, we found that there were 2 frequencies, right, that we found, and it was, let's say, at this value, there was 1, and at this value was another one, right? Let's say. So with order 10, now why are these two? Because we already discarded the other 5, right? Based on what? Too high a damping and too low molar collinearity. Now imagine that I do this with order 12, and then with order 14, and then with order 16, and with order 8, and with order 6, and it doesn't have to be even numbers, because if we put an uneven number, then what happens is that there's going to be some pole that is real, but that we will discard it in our discarding criteria, right? So if we do that, we will get a plot, and maybe the plot will be like this. And then maybe over here we find and then maybe here we find something like that. So this would be a stabilization diagram that tells us what? That frequency 1, this value, is pretty stable, right? Because no matter what the order we choose, we always find it, and we always find it more or less at the same value, right? Could be a little bit of difference, but not much. Frequency 2, you know, you need at least this order, but once you find it, it's kind of stable also, right? This frequency 3 requires an order that had to be 12 to start seeing it, let's say, right? Let's say this was 12 here. I couldn't see it with 10, but once I put 12 or 14 or 16, it's pretty stable. So I think that's probably pretty good too. Remember, all these points already satisfy damping and modal collinearity. And then there is this one here, 4, which appears to show up, but then as soon as I put an order a little bit bigger or smaller, it's not true. So this one would be not encouraging, right? So we probably would not use that one, right? So a stabilization diagram is simply a plot of the results of the identification for many different orders after cleaning it up. And from visual inspection of the interaction of the stabilization diagram, we select the poles that we want to keep. Okay? In your code yourself, for example, I can't remember exactly, or maybe I can. Let's see, what is it? We have a program, let's say DBN talk or something like that, right? That calculates the Markov parameter like things, right? For the case of output only. Then we have DBN what? Hankel? That gets the Hankel matrices, right? And then we have DBN ERA or something, right? That gives us the A and the B. So you could put those 3 programs in a loop, right? For J equals 1, or not 1, for J equals, you know, 2 to 30. And J is the order. So for example, you could make a few little changes, or I think it's a little change here in the Hankel when it selects what is the order selected, which is just the order of the loop. So the point is that you could write a little program that runs this thing and calculates the A1 and the C1 in cells. So this is a cell, and this is a cell. So there is A1 for order 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 30, for example. I mean that because the way my stabilization diagram program works is that it outputs the stabilization diagram, but the input is the cells of the A and the C. Okay? So I don't know for sure whether we'll use it. I think I would like to try something so that you can use it, but you will have to write a little code that actually calculates for all the orders. I mean, you could do it manually, but it's ideally to just simply create a little loop so that for all the orders that you want to inspect, you get the A and the C. You don't have to make any decisions. You just simply pick that many singular values. And then once you have those two things, you run the stabilization diagram that I will give you, and it'll come out with this plot. Okay? All right, so we'll call it a day for that one, and we'll continue next time to perhaps explore the usage of the stabilization diagram, if by then I haven't posted for you, and also provide some theory so that you can understand under what conditions the model collinearity index may fail.